Alright, so we're looking at evaluating limits analytically, and this particular one here, of course, it's on this section here, and we're going to be looking at some direct substitution, or if we get 0 over 0. So as you can see here, if we plug 6 directly in, the uh, the the denominator, we get 54, and then minus 1 is 53. Let's just hit the help button here and see what happens. So we're doing this direct substitution, as you can see, and we're not getting 0 over 0. So that's good, because that means that we don't have to factor the numerator and cancel like factors out. But how would we factor the numerator? That's the question. If we were to get a number here that when we plugged it into the denominator and we happen to get 0 down here, we need to know how to factor this up here. So let's just go ahead and go to the whiteboard and check that out. Alright, so we have the limit as x approaches some number here. I guess we should use the number that we've got in the example, and the number is actually 6. So we have 9, right, and I've got a parentheses around this for a reason. Of course, everything's for a reason in life, and that looks like a 4, but let's round that off there a little bit more. So we have 9x minus 1. Now, 1 squared is 1, so we can kind of consider this 1 here to be a square. And so if we wanted to factor the numerator, we could write 9x minus 1. Now let's put a parentheses around that. And then 9x plus 1. And if you multiplied this out, we should end up getting this back. Now let me just say something here. I put a parentheses around this and then squared it for a reason. If this were written 81x squared, which you're going to see here in a minute in another problem, over 9x minus 1, you're going to need to know that, of course, 81 is a perfect square, and that you'll want to write it like this. Okay, so you'll more than likely see it like this in a problem and not like this. All right. And of course we have 9x minus 1, and the limit as x approaches 6. Now we don't have to factor this, but we are doing it anyway because this number right here, when we actually go to evaluate it, for example, if this were 1/9, if this number were 1/9 and we plugged it in, we would end up getting a 0 in the denominator, and we'd also get a 0 in the numerator. And because and the reason for that is because in this particular factor here, if I were to plug in a 1/9 into the x here, we'd have 1/9 times 9, which is actually 1, and 1 minus 1 is 0. And we'd get 0 over 0, and of course that's not good, and so we'd need to factor it like we did here. And of course then what we want to do is cancel out our like factors and rewrite this limit. Now of course, like I said, we're only using 6 and this is not necessary, but it's okay. We're still going to get the same answer. And of course we do the direct substitution here, and we do 9 times 6 plus 1. Right, 9 times 6 plus 1. And of course this is 54 plus 1 is 55 for our final answer. But the whole idea here is you need to realize that we can factor this thing, cancel like factors out, and then get a new limit, right? But this old limit is still equal to the new limit, and then do our direct substitution last. Even though it's not necessary in this problem, but you will see where it is necessary. So that's why I'm reemphasizing this over and over again.